name is Aditya Anand. I will be talking about how to do program analysis for managed runtime in presence of dynamic features. So before we start, let me briefly give you an idea about how program translation works in Java. So we have Java code. We give it to a static compiler called Java C compiler, and we get the Java bytecode, which is the machine independent code we all know. This bytecode, when given to the Java virtual machine, the execution first starts by first interpreting the bytecode and getting the output directly. In between, based on some threshold values and some other heuristics, the JIT compilers are invoked. And those JIT compilers directly produce the native code which can be used in further execution of the bytecodes which got JIT compiled. So this is how the JVM uses interpreter and JIT compilers to generate the bytecode. If you look closely, the JIT compilers, the brief idea about JIT compilers is that it takes certain bytecodes, convert it to some form of IR, and perform several optimizations, and then give you the native code. In the today's morning keynote, we looked into several optimizations that can be performed in object-oriented language. One such was object allocation. So in Java, the object by default gets stored on heap and get freed up by the garbage collector. We all know that. So we have a statement like a equals new a. The objects will be by default on heap. The advantage is that it unburdens the program. Programmer need not worry about the complex allocation, deallocations, decisions, and it will reduce the further possibility of having any harmful memory bugs. But the challenge from the VM perspective is that if the object is on heap, the access time becomes higher, as we will have indirections while accessing the object. As well as from VM perspective, the garbage collection is an overhead. So what's the solution? We saw one of the solution which was stack allocation. So we can allocate objects on the allocating method stack. Advantage will be we will have less access time as we can directly access the object on the stack, and we need not worry about the explicit garbage or explicit memory deallocation or by getting it freed by the garbage collector. But can we stack allocate all the objects? The answer is no. So to get the list of objects that can be stack allocated, we use an analysis called as escape analysis. It basically gives you a list of objects, or it helps you to get the list of objects that can be stack allocated. But in case of Java, as the analysis or the optimizations are performed during JIT compilation time, and these JIT compilations are done while your program is actually executing, most of these analyses are imprecise, and because of which very few objects get stack allocated. Now how to improve this situation? One could suggest we can, if we don't have time at the runtime, we can't do the precise JIT compiler analysis, why not do static analysis? We can perform context, flow, field, escape analysis statically, and then use the statically generated result at runtime and can get a lot of objects on stack. Note that if we are using static analysis, we might be doing it optimistically, because there are features like dynamic class loading, hot code replacement, callbacks offered by the language or the VM, which might affect your static analysis result. And because of which, statically with the list of objects which you marked for stack allocation might not get stack allocated, or it will be getting stack allocated wrongly on this stack. So we will see these features one by one. What are the challenges with these features? First is the dynamic class loading. It basically allows you to load a new class at runtime. Even it allows loading Java code at runtime that was not known before program execution started. And for that, it uses the reflection API. Basically, you can get the class name and the method name as a string format, and you can invoke any method at runtime which was not known statically. Let's see a concrete example to understand it a more better way. So let's say we have a class here, class A, which has three methods, foo, zar, and bar. And then we are creating three abstract objects pointed to by reference variable x, y, and then access field points to O6 object. At line 7, the reference variable p points to object O6. Now at line 8, we have call to method bar. In that bar method, if you notice at line 13, we are just storing the second parameter in the first parameters field. So we got an edge from O6 to O5. And at line 9, we are calling to method zar, which is not making any change to the points to graph of the method foo. So this is what the points to graph will look statically. Note that any object O4, O5 or O6 is not getting accessed outside the method foo, which means that statically we will say that all these objects O4, O5, O6 can be stack allocated. Now suppose at runtime, a new class gets loaded. Let's say class B, which extends class A and overrides the method zar. And this method, in the method zar, we are doing this q.f equals p. If you notice q is coming as a parameter to method foo, which means that now q on its field f can access the object O6, which means that if we stack allocate object O6 and O5 using our static analysis result, we will have incorrect stack allocation. So this is a challenge in presence of dynamic class loading. Similarly, we have feature like hot code replacement, which allows to change your code at runtime without needing to restart your execution. It is mostly used during the debugging, and most of the modern IDEs like Eclipse, IntelliJ provide this feature. The possible change during hot code replacement is just modifying the method body. You cannot add or remove methods, modify class hierarchy, etc. But by just modifying method bodies, still our static analysis can get affected, and we can have similar problems like hot code replacement. Let's say here at line 15, we put a debug point, and earlier which was not doing anything relevant to method foo's points to graph, now we add the same statement here. And again, we will have same problem which we had during our hot code replacement. And we will have, again, incorrect stack allocation. The third feature, which is callback. So callback allows you to invoke application method from a library method. And our interprocedural static analysis required a complete, precise call graph. But in application, we use a large number of third-party libraries. And statically, we don't know if there exists a callback edge from those third-party libraries to our application. So our call graph at static analysis time will be imprecise. And again, we will have an issue of unsound stack allocation at runtime. Yeah, so just to see with an example, let's say statically we had two methods foo1 and foo2, which is calling the method bar. And at line 5, we are just storing the local object O4, which is pointed to by the variable A in the parameters field. Statically, we will say that the call graph will look like this. Foo1 and foo2 is calling the method bar. And we will say that, okay, O4 can be stack allocated if bar gets in line with its caller. This is what we will statically generate. But at runtime, if a third-party library passes an skipping object to this method bar, at this point, the result which was generated statically saying that it can be stack allocated at runtime in its caller will be wrong. If we allocate object O4 on stack frame of the method lib, it will be wrong. The other challenge, or I say the problem which we have with static analysis is that how to say that your static analysis is sound. Like we can miss some corner cases, or if we are passing the static analysis result to the runtime, somebody can alter that static analysis result. So in presence of all these challenges, how can we use static analysis result at runtime to allocate more number of objects? So basically how to use static analysis in the runtime in presence of all these challenges. To solve this problem, we came up with an idea which we call dynamic heapification. So just recall this example where we had a stack allocated object O5 and O6 on stack with our static analysis result. So suppose this is the situation where we have stack allocated object. The first thing which we do if we find that our stack allocation is wrong is to heapify, basically copy the objects back from stack to heap, and then recursively copy all the objects that are reachable from that heapified object by maintaining the field relationship which they had on the stack. And then next, we correct the reference which was there from object O4, in this case O4 to O6, from stack to heap. Similarly, for the reference variable Y to O5. So this is what we do if we find if we find that we have wrongly allocated object on stack. One question which will come to mind is that how do we identify we need heapification? So for that, we put heapification checks. We do it for all kind of statements that can change the status of an object, like return statements, store statements. Let's see this brief pseudo code kind of thing for a store statement. Let's say we have a statement a dot f equals b, where the RHS object is the object pointed to by the reference variable b, and the LHS object is the object pointed to by the reference variable a. If at this point we want to check whether storing the RHS object into the LHS objects field requires a heapification of RHS object. So RHS, first thing which we check is whether RHS object is outside stack bound. If it is outside stack bound, we don't need to heapify. If LHS, then next thing which we check is whether LHS object is outside this stack bound. That means it's on heap and we need to heapify. If we reach to this third check, which means that both the objects are on stack frame, then the only check which we do is whether LHS object has longer lifetime than the RHS object. Yes, so we do this check, and if we find that LHS object has longer lifetime than the RHS object, we heapify. So at a store, the simplest case here will be that both the LHS object and RHS object are on the same stack frame. We find that okay, they are on the same stack frame, we don't need to heapify. But what if they are not local, they are not in the same frame? Let's consider this case where we have method M1, M2 and M3, where M2 is calling, M1 is calling M2, M2 is calling M3, and M3 we have this store statement. The first scenario will be in M3 we have this statement, the object OB which is pointed to a variable B is in method M2 and then OA is in method M1. In this case, what we will do, we will walk up this stack and then find out, okay, OB is in method M2, it is allocated in method M2 and OA is in method M1. And here OA has higher lifetime than OB and we are storing OB in OA. That means that we need heapification. So OB escapes and we need to heapify. Similarly, the case will be exact. If the case is exactly opposite, we don't need to heapify. And then we have the third case where both are on the same stack frame. In all these cases, we will walk up this stack and then find out where exactly the object is. So we are doing something which is this stack work, which is quite costly. We don't want to do it for every store statement in the program. So to solve this challenge, or to make our heapification check efficient, we can see that, okay, we can actually compare the addresses of the object which are there on the stack frame. So we can just compare whether the RHS object has higher lifetime than LHS object. In that case, we don't need to heapify. So that will satisfy the first case as well as the second case, as we can compare the stack addresses of the object. But in the third case, we can't guarantee. So to guarantee and to use this efficient check, in all the scenarios, we proposed another idea, which we call stack ordering. So what we say here is that simple address check should work majority of the times, and along with generating the list of stack allocatable objects, we also generate ordering among them. So we use the points to graph idea, and let's say if we have object OA pointing to OB, we say that OB should be stored first and then OA. So this stack ordering idea we use, and this is how we allocate objects on stack. And this reduces the heapification check, and majority of the times we will be using that simple conditional check. Of course, in case of cycles, we will have, for the package, we still be doing stack walks. Quickly coming to the implementation and the evaluation part. So we implemented this static analysis in Suite and runtime component in the OpenJ9 VM. We used several Decapo benchmarks and the spec JVM 2008 benchmarks for our evaluation. And we have two schemes, basically base and the opt. And we compute basically the enhancement in stack allocation with our scheme. And then what is the impact on performance as well as garbage collection. So just quickly tell you, this is basically a table which is telling us what are the different numbers for stack allocation. So we have static count, we have dynamic count, we have stack bytes. Static count basically gives you the allocation, basically the number of allocation sites which got stack allocated. Dynamic count basically is the actual runtime objects that got stack allocated, and the stack bytes is the actual number of bytes that got stack allocated. So if you see for benchmark like H2 here, you can see the static count increased from 61 to 94, but if you see the dynamic count, it increased from 29 million to some 452 million. We saw similar improvements for other benchmarks as well. And overall, the stack allocation improvement was 71%, and the stack byte improved by 54%. Yes. Just to conclude, we also see similar improvement in our performance, and the overall performance improvement was around 8.8%. We saw degradation in the garbage collection cycle as well. The number of garbage GC cycle reduced by 5.3%. So to conclude, we handled an O optimizations of allocating method local objects. We ensured functional correctness in presence of these dynamic features as well by introducing the idea of heapification. And overall, this was one of the first approach to soundly and efficiently use static analysis in the static analysis result in JIT compilers. Thank you.
Thank you. This is a good work. So obviously, because the last bit was a bit fast, you said there's 8.8% performance improvement. But I wonder if there are benchmarks for which the stack walks and the heapification leads to degradation in performance. Is that something you observe?
No, we didn't observe any degradation with. So we try to be as precise as possible in our static analysis so that we don't see any heapification. But of course, we can go more aggressive statically, and in that case, we will see heapification.
I see.
But we try to also measure what is the heapification cost. We try to put like explicit wrong result in our static analysis result, and then like let's say for like we saw like for a million heapification, we saw degradation about 10% in the performance.
I see. Okay, thank you.
Hey, thank you for a nice talk. I have a slightly different question, not on the optimization side, because you are dealing with memory and you are trying to reduce some kind of memory usage. Have you thought of the power requirement drop that's going to happen when you try to remove the memory requirements? Specifically, have you run your stuff on spec power to see whether you're also reducing the power requirement?
Sorry, I didn't get your question. Spec for okay, power requirement drops. Okay.
Yeah, so because you are going to access less memory, right?
Mm-hmm.
You are not to put it on the heap and stuff like that. Maybe you are doing scalarization and stuff. Your power should reduce. And we know that Java, especially Java, is very, very high on creating very small objects with short lifetimes, which increases the power requirement when the benchmarks and all these workloads are run. So have you done anything after you do your optimization? Run some spec power workloads to see whether you are dropping on the power requirement.
Okay, yeah. So we explicitly don't do anything like we didn't evaluate based on the power consumption. But I feel like we can actually include that thing like to measure if we have done our if we are doing this much stack allocation, what is the power reduction? I feel.
Yeah, so if the lifetime of the RHS is longer than the lifetime of LHS, then instead of heapifying, sorry, I think the other way around.
No. It's exactly opposite. Yeah, if LHS has the higher lifetime, yes.
So instead of heapifying, you could potentially allocate it on the higher stack, right? Like shift it to the higher stack instead of shifting it to the heap.
So if LHS has the higher lifetime than RHS,
Yeah.
in that case, what do you suggest?
Instead of heapifying the RHS, you could potentially shift it to the higher stack, right?
But that way we will be changing the way the object is being accessed to, right?
Yeah, but you are changing that anyway by moving it to the heap.
No, so we are not changing the way the program is behaving. We are just changing where it is being allocated. So instead of accessing it from stack, we are accessing it from heap.
Okay.
If you have any further question,
Yeah.
we can discuss on.
Thanks.
So I had a doubt because you explained that you put the object on the stack, right? So I wanted to know how you decide the lifetime of the object while you're going through the code. So do you do that during runtime or is it like done somewhere else?
So lifetime is basically decided whether the object is being accessed outside the method or not. If it is local to the method, it has just the lifetime till the time method is there on the stack frame.
Okay, okay, okay.
Yes. Yes. Yeah, and we decide this the lifetime of the object statically itself. So at runtime we don't do it.
Yeah, you said walking the stack is expensive, but if everything is allocated on the stack, can't you just compare object addresses to the frame pointers?
If everything is allocated, like I didn't get again.
So you said like walking back the stack is expensive.
Yes.
So instead of walking up the stack, can't you just compare object addresses to frame pointers?
Hmm. Yes, yes. So we do that. No, that's what we are comparing. So we have a slide where we are comparing the addresses of the object itself. That's what we come. We don't. Yeah, we don't store the frame pointers anywhere. Yeah, we don't have frame point.
Information. Doesn't the runtime have this information? Like, oh, okay. I thought the runtime always had this. No, okay.
Thank you.
Thank you, Aditya. Thank you very much.